Is this good for the camera? Am I in shot? So as she said, my name is Nathan. Last name is Greeneltch, tough to say. I'm a consulting engineer at Intel. I'm going to talk about the data analytics acceleration library that we have called DAL for short. This is a performance library. It makes sense, right? That's what Intel does. It's fairly new. It's free and open source. So we like to take these chances to introduce it to people that may not have seen it before. So as I said, it's an analytics library. It's performance-based. It focuses on what's now called classical machine learning because deep learning is its own thing, I guess, now. So this is things like vector machines, random forest, penalized regression. As I said, it's free and open source. We do use some other libraries underneath, and if those aren't open source, then obviously you can't see that code, but the rest of it's free and open source. Indiana has a fork, as I understand, and they are contributing currently to the library. And anybody else can do the same. We have APIs currently for Python, C++, and Java. We're working on a new higher level API. So it's a one-liner type job because we know data scientists aren't always the best programmers. They have other things they need to worry about. It's important to note that DAL is not competing with other frameworks. We're Intel. We build fast primitives, fast math functions. So we're just as happy to put our math underneath somebody else's framework. We already have customized version of TensorFlow, some MLlib functions, a whole accelerated version of scikit-learn that we give away for free on Anaconda. And we'll continue to put our math underneath other frameworks, but we do have APIs if the user would like to use the DAL library directly. Because we're Intel, we have hardware and software, of course. A lot of people don't even know we have software, but our fab is here, and right down the street, we have software engineers. We know a lot about what the hardware looks like, what it's going to look like, but we know what the roadmap is. So we always build in accelerations ahead of time. So if you use our fast primitives, fast libraries, and then you buy new computers, we should already have that up and running and utilizing your hardware. So DAL itself has 3 processing modes. We have a batch and offline mode. This is when you're lucky enough to hold all your data in memory and just process the whole thing in one fell swoop. We also have online or streaming processing mode. This is on-the-fly processing, right? So you have a small amount of data, you build an initial model, you bring some more data in, and you incrementally build it up and build it up and build it up. We also offer a distributed processing mode. This is, as it sounds, you have multiple workers. They contribute their work and send it back to a master, and the master reduces it all. And this is out-of-box support for all of these modes. So we've written our algos to be compatible with this. So this is some nuts and bolts. We stay current with all, as I said, hardware that we know is coming up in the roadmap, and all the latest instruction sets are covered. So if you buy AVX 512 hardware, we will utilize your registers as intended. We internally, underneath the hood, we rely on MKL primitives, the math kernel library that many of you are probably aware of. It's very popular. And the important note here is that DAL uses Intel TBB threading exclusively. So we use our own threading building blocks library. If you're used to other threading, unfortunately, maybe you'll have to learn a little bit about TBB. Like I said, we have distributed and streaming modes. DAL has data sources that are ready for this, right? So you don't have to bring a data source in from somewhere else. We build them so they're ready to go in a distributed and online fashion. That means they support partial results, merging, serialized, deserialized, these kind of things. I don't know if we'll be able to see it in the other room, but this slide shows currently what methods we have in the transformation side of things. I'll leave it up for a second.
So, my actually, I'm picking up the yellow definition algorithms.
Yes. So these ones we have full all three processing modes in. So I should say, I meant to say it earlier, this is a far from mature library, right? We're fairly new, that's why we're introducing it. We're at the rising edge of what's going in this library. So that's a hint that if anybody would like to talk to me, if they've used it, give me feedback or what they want to see in the library, it's going directly back to the engineering team, and it will contribute to the way the library looks and feels. That's where we're at. That's where we're at the moment. This is the machine learning algo side of things. This is what's inside the library as of now. Decision forest is random forest. We just call it decision forest. And you see these say new. Like I said, we're on the rising edge. We're adding things with each release. Because we're Intel, I have to show benchmarks and show performance. So I'll start with a decision forest or random forest benchmark. We have single-threaded and multi-threaded. If you look at the right side with the multi-threaded, you can see we're at orders of magnitude speed increases. This is just out-of-the-box DAL. If you understand and learn the API and use it, you'll get these accelerations. This is a comparison to scikit-learn in Python. This is relevant because, as everybody knows, Python machine learning is moving at a breakneck pace, going up every quarter. This is compared to the easy-to-use scikit-learn library. Of course, we are a little bit accelerated compared to them. As I said, we don't compete with frameworks. So we have our own version of scikit-learn where wherever possible, we throw our math underneath. So you can actually bring the scikit-learn bar down to DAL without even knowing you're using DAL if you get our version of scikit-learn. And then the final one is just a basic PCA transform. Again, we're orders of magnitude faster. On this plot, this is log scale. I had to plot it that way because the accelerations were so large. We don't need to get into the code, of course. I don't know what audience I had when I arrived. I just want to show sort of the what I think of as the ease of use. So don't get into the weeds of the code. The important part is here. So we have, as I said, DAL has data structures we give you. We call them numeric tables. So you start by loading up a numeric table, create an algorithm object, set your input and your parameters. This is where you would build a grid search. Compute, get your result, and then use DAL's built-in serialize to serialize the model. Then you're ready for deployment prediction. Prediction side is very similar. You do the same thing. Get your table, load up your data, create a prediction object, deserialize the model using DAL's deserialize function. Then it's all the same. So I want to stress that these are all DAL methods. So we've given you enough to do end-to-end analytics if you'd like to stay in the DAL library. I'm going to cover a quick usage example. This is from a customer that came to us. You can imagine some oil rigs, remote rigs with edge devices on them, so little computers here and a little computer there. And they're constantly collecting data, generating data, sending it back home to do some analysis and decision making. Currently what the company was doing was loading grabbing a bunch of data and dumping it all at once, and then grabbing a bunch of data, dumping it all at once. And back home, they would wait for all the data to arrive and then start trying to build some models for some sort of predictions. The downside of this method is, number one, you're overutilizing your communication bandwidth, right? You're just dumping a ton of data in spurts. And number two, you're underutilizing these edge computers, these devices, right? So these are computers, they can do work as well. So the communication bandwidth issue can be addressed with the online processing version. So I guess the stress here is that DOL makes this easy. So we have a data structure that's ready to be used for partial results. We have a partial compute method. We have a partial result method, and then a finalized compute. So this result can be finalized at any time. You can keep going as many times as you like and finalize it whenever you want to use it. This is what the API looks like. This is an example of the Python version of the API. The important part here is just when you load up your PCA algo, you load up the online version of it. That's the only difference. And then you use the API as you would in batch mode. The other solution, of course, is the distributed mode, just as it sounds. We want to actually utilize the computers at the edge. So there's some computer here. There's a partial compute you can use there, partial compute you can use there. Send your partial results back at home, and you're ready to just finalize them. So this is DOL data source, DOL method, DOL object, DOL method. So it's all there inside our library. So we'll look at this API again. It's the same story, works very similar to batch. You just have to load up the right object. There's two sides to a master worker paradigm, if you've ever worked with distributed processing. So this is step one, the worker side. The way you tell DOL you're doing that is you load up the distributed version of the algo and you pass the argument step one local. Local means worker. And then everything else is the same. We get onto the master side. Now you make sure you're at the right rank and you load up step two master as your argument, and now it knows it's the master node, and everything else is the same. So it's very easy to use. Again, this is Python. Before I get into this, I said earlier we're working on a higher level API. We're not trying to compete with sklearn or any other similar libraries because we're underneath those. But with a high level API, you'll have a single line fit. All this boilerplate would put into a single line, and you would say something like distributed equals true, or distributed equals false, or online equals true, online equals false. And it should do all this for you. So that's in tech preview. We're looking for people to try it if you'd like to work with our one-liner version of the API. Now I'm going to get into sort of a preview of what's upcoming in the library. This is a beta that's going out. It's not even out yet. I don't know when it's going to come out. There's testing that's holding it up at the moment. And I want to highlight a large addition to the DOL library. So we said we were end-to-end analytics, but we were a little bit weak on the pre-processing side and the transformation side. So coming in 2019 beta, whenever it's out, we'll have a beefed up version of this beginning part that's highlighted here. So we'll have loading and filtering and transforming all in a new portion of the API that's unified. So it's basically, it feels like all the same step. Just because this is an iterative process, right? A data scientist needs to be able to go up in the abstract, make some decisions without worrying about all this programming, and they don't need to care that they're filtering or they're transforming as far as programming goes. They just need to care what it looks like plotting and making decisions, right? What we've done is included a bunch of fast pre-built modifiers, transformers, these kind of things. We'll call MKL when needed. We'll have our own parallelism we write into it. But we also allow for custom modifiers. So you write your own function in any way you'd like, and you can just pass that as one of our modifiers. This whole thing was built with an eye towards concurrent loading compute, which I'll show at the end. That's not actually in the library yet, but that's what we're pushing for with all this work. So just an example of how easy this is. You load up your modifier object, and you just list which features you want to transform, and then what transformers you want. And then you hit go, and you let it run. If you want to do a custom version, you define your custom object, put your math right here, your custom function, and then when you use the feature modifiers, you just call your custom function. Here it's my square modifier, but it's just something that you write yourself. And then everything else is the same. So this is in the beta, and this is where we're all pushing. This is what we're pushing towards. So like I said, concurrent loading computing, so IO's very slow. So we want to compute, transform, filter, all these things at the same time that the rest of the data is loading. So you load up some, compute, load up some, compute. we already have it working. Of course, we have some pre-benchmarks, but it's not ready for prime time yet, so it's not in the library. I said there's a free version of this, or there's a standalone product. You can download the standalone version of Doll, or you can download it with our huge Parallel Studio suite. Please get involved with the beta program if you're interested. It's coming soon. I don't know the date, I'm sorry. And like I said, this is not fully mature library. We want feedback as much as we can get, so come talk to me. If you've used it, complain all you want, and we love to hear that. If you don't want to talk to me here, you can email me, and it's my email address. And that's it. That's my 5 minutes, yeah. So I have 4.5 minutes for questions if you have any.
Okay. So maybe we should, we keep on time very well, just 1 minute is on. So maybe we should move on to the next speaker, and then followed by our 30 minutes break.
Okay, do this without making lots of noise.